Okay, thank you. Yes, thank you very much. I'm going to present ACTS track reconstruction on GPU and the ongoing accelerator R&D effort in ACTS. So even though this might be well known, a bit of an overview about the ACTS project and the challenge we face. So ACTS is an experiment independent tracking toolkit written in modern C++, and it contains efficient implementation of common tasks that you would need for track reconstruction, like seek finding, track fitting, and so on. And it's inherently written in a thread-safe way by keeping states and configs per thread state. And it uses, during the track reconstruction, its own tracking geometry description, which is a bit simplified towards a full geometry description as you would find in Geant, which saves already quite an amount of CPU resources. And it's also adding a simplified material description to it, which is basically based on radiation length and nuclear interaction length, instead of describing material to great detail. All right, and then knowing, as we probably all do, of the compute resource shortage projected into the future with continuous budget models for the high luminosity LHC, also ACTS is looking into research on accelerating the track reconstruction chain with, for example, GPUs. So for this to succeed in ACTS, there has to be defined a suitable event data model to save the data, like cell activations and space points, measurements, and so forth. And then the tool chain has to be able to run on in-device code, for example, CUDA kernels. And as I just mentioned, the tracking geometry, we also need a GPU-friendly implementation of that tracking geometry in order to model our detector also on device. And this includes a magnetic field description too. Okay, so a quick overview of the track reconstruction pipeline that we need to adapt. So this all starts out with cell activations on our sensitive detector modules, for example, pixel or strips, that need to be clustered together, belonging to one HID, which then forms a measurement in that particular module, which consists of the module local position and the variances. And then from each one of these measurement positions, a global space point is formed in the 3D coordinate system of the detector, so XYZ usually, which then is the input to the track seeding, where 3 of those space points are grouped together to form the starting point of the track finding. So from those 3 space points, initial track parameters are inferred, with which you could parameterize a proper helical trajectory. And then this is forwarded into a combinatorial Kalman filter that adds more measurements to this initial track state by testing out a lot of combinations of measurements to add. And then those track candidates are fitted with an additional Kalman filter step to provide the final track object. All right. And then previous to the dedicated R&D project, there have been some pilot studies in ACTS on GPU computing, and one big one was to adapt the ACTS Kalman filter to GPU and use it for track fitting. So in the sequential track fitting model, there's an almost linear rise in execution time with number of tracks, and then parallelization with threads on tracks, and also inter-track reconstruction parallelization has been tried. So for example, with intra track parallelization, I mean parallelizing matrix operation doing the reconstruction of a single track, for example. Both of these have been investigated, but using a simplified telescope geometry, so not the entire ACTS tracking geometry. I come to why in a moment. And there were some nice speedups found, like 4.6 in events with more than 1,000 tracks on different hardware. And using, I believe, a custom-made matrix implementation, because back then there were some issues, I believe, with porting eigen, which is generally used for linear algebra implementations in ACTS, to device. And then, yeah, as I already mentioned, there was a very simplified telescope geometry used. I don't know if you can see my mouse cursor. So there's a picture of this on the right, which is just a sequence of planar surfaces that were unbounded, so that every next step in the propagation would actually also hit the surface. So there was no thread divergence in this sense. And the reason for this is that the geometry description, which is usually polymorphic, cannot be generated on the host and then copied to device, because this would invalidate vtable pointers, and also if this is built in a vector-of-vector structure or in a tree-like structure, would also invalidate pointers in those data structures. So this was one major problem. And then there was also a study done on track seeding implementation. So there's a CUDA and a SYCL implementation. And the main problems there were that the number of final track seeds is not known beforehand. And since memory needs to be allocated before the kernel is launched, it was essentially the worst case scenario expected here, and this resulted in a huge memory allocation, and in the end in a fairly inefficient implementation. And so in ACTS there was this dedicated parallelization R&D project launched that would address many of these issues, and this is divided into a number of little sub-projects. So we have the algebra plugins project, which wraps different linear algebra implementations for our vector matrix operations that we need during the track reconstruction, so that in the R&D projects we can actually switch out the algebra implementation underneath the hood. So now we can actually replace eigen against, for example, handwritten array-based implementation. Then there is VecMem, which is a library that enables us to do memory management on vector-like structures between the host and the device side. And this also provides support for different compute backends like CUDA, SYCL, HIP, and so forth, and abstracts this nicely away from the client library. And then there is TrackCC, which is the main repository for the track reconstruction chain demonstrator. So this is where the steps in the track reconstruction pipeline that I showed earlier are implemented. So clusterization, seed finding, space confirmation, and so forth. And this will allow to benchmark this track reconstruction chain in a realistic setup in the end. And yeah. Playing into this realistic setup is the DETRAY library, which provides the device-friendly tracking geometry description, also provides the track state propagation through that geometry, and also fairly recently, it has added ACTS-inspired material description to that tracking geometry. And then we have Coffee, which in turn enables the DETRAY track state propagation. So Coffee is a library that describes in general vector fields in a compositional way, and makes them usable also on host and device. And in that way, it's going to be used for the magnetic field map and interpolation. And on the right, there's a nice little chart that shows which project is used by which project. So we have algebra plugins, Coffee and VecMem as the most basic and technical projects, maybe being used by the implementations in DETRE, and then later on in TrackCC, where everything will come together. All right, so a bit more on algebra plugins. So as I already mentioned, this is used for the linear algebra implementation, both in DETRE and TrackCC, and it wraps itself around external linear algebra libraries, but it is tailored to what we need in the linear algebra during track state propagation. So it will not go beyond a matrix size of 8, for example. And it is separated into backend implementation, where we can define how the memory is going to be used. So is this an STD array backend, or do we use eigen-based storage? And then we have the front end that defines more or less the interface in for the mathematical operation. So we can use an eigen native interface, or we can use, for example, a C array based interface to operate on the eigentypes. And then these algebra plugins can be switched out in DETRE and TrackCC at compile time, and then we can recompile this, for example, with a naive handwritten algorithms on top of STD arrays, or using the eigen implementation of, for example, matrix inversion. And in this way, we can then benchmark our tracking chain with different linear algebra implementations, and we can benchmark them in a realistic setup instead of only doing micro benchmarks on the algebra libraries themselves. There's a little support matrix of what we currently have in algebra plugins. So CMath is the STD array based self-written linear algebra implementation that I mentioned. Then we have eigen, and then also on for CPU at least we have an S-matrix implementation, and then at least for the 4x4 affine transformations that we use in the geometry, there's also a explicitly vectorized version using VC, but this is not actually supported anymore, as we ran into some troubles in extending this to 6x6 and 8x8 matrices in the higher dimensions. All right, and then there's VecMem. So the VecMem library provides memory management for us by making use of C++17 polymorphic memory resources. So in this way, we can determine where and how memory should be allocated in our in the containers we use in our projects. And since this is polymorphic, this can be decided at runtime and customized. And those memory resources are even composable. So you can, for example, use a memory resource that allocates memory on a device, like a CUDA device, and then add a downstream memory resource that modifies the behavior of these allocations. For example, in an ARENA allocator, you can allocate a huge amount of memory and then give out little portions of it. And then VecMem also provides us with an STL-like interface to that memory. So on device, for example, STD vector doesn't work. So from VecMem, we get the device vector class, which exposes the same interface for us, so that we can essentially keep our core implementations and then template on the container type, but use the same interface. And the data then is transferred from the host, where the vector is allocated with a resource, over a lightweight view object, essentially contains a pointer to that memory as a parameter to the device, to the kernel. And in the kernel, then the VecMem device vector can be instantiated by passing the view to the constructor. So this allows for a nice abstraction from the for the memory management from our core library implementations in TrackCC and in DETRE. So this is heavily used in the TrackCC event data model, and also in the fairly involved data management in the DETRE geometry implementation. All right, so coming to TrackCC, as I said, this is the chain, the demonstrator chain for the track reconstruction in CPU and GPU. And it is working on adapting ACTS like track reconstruction in a heterogeneous design. So using providing host and device implementations, but without any kind of compromises in the complexity of the reconstruction or in physics performance. So this is not in a simplified setup, it's going into full detail. And TrackCC already supports a number of backends like host CPU, CUDA, SYCL, and I believe there are some implementations also in Futhark, and I think also Cocos already available. And also comes with a nice support matrix where we can see what is implemented where. This is available on the TrackCC repository actually. So on the clusterization, we have connected component labeling essentially supported over all backends, as is measurement creation. And then space point formation is the last point, and the track finding implementation is basically available for CPU, CUDA, and SYCL already. What's missing right now is the combinatorial Kalman filter for the last step in track finding, and the track fitting Kalman filter step is also not yet there, but it's work in progress and has seen some nice progress recently, actually. All right, so the first step in that pipeline would be clusterization. So this is orienting itself on ACTS, where we have connected component labeling, and the clusterization in TrackCC then runs the forming of the clusters and the creation of the measurements on every module separately. So a module in this case would be a sensitive detector surface. And as input, it uses simulated hit data from ACTS, where the data is then interlinked by the ACTS GUID, which is also used internally in TrackCC to identify the data. So it's not making use of the dead rate geometry there. It's a fairly simple mapping still. And then after the clusterization, the final step, the space point creation is also there. It currently does the local to global transformation on the measurements, but I believe it's not handling strip-based space point creation yet. Somebody may correct me. So for this, it's using a sparse CCL algorithm, which essentially goes over the pixel matrix and assigns a common label to neighboring cell activations, which then form a cluster. And it's doing this in two passes. First, assigning a temporary label and then establishing which regions of these labels are connected. And then in the second pass, it will create the final cluster labels. And this works out quite well, or yeah, it's quite straightforward to do on the host side, because there we have fairly flexible dynamic memory allocations. But on the device side, we kind of need to know beforehand how many cells, clusters, measurements, etc. there are. And this has led to a split up of this into different kernels. So first, it will run a find cluster kernel where the actual CCL labels are filled into an initial vector structure, where the label is essentially the index for a cluster. And then from this CCL table, equivalence table, we can then infer how many clusters we have, to then go into the next step and assign allocating the data structures we need to save the clusters. Then it continues on with counting the number of cells that would be needed per cluster. And then finally, when we have all of these information, we can then allocate our final container where the clusters are present and all of their cell information is filled in. So yeah, this has been, I think, a big challenge on the GPU side, but limiting the memory in these allocation schemes, I believe, is still faster than doing the brute force implementation that has been done also in the seed finding later on, which has been seen in ACTS before. Okay, so coming to this seed finding, this actually we'll see quite similar in this regard. So in the seed finding, TRACS-CC is using a 2D regular grid that is set up over the detector volume and then populated with the space points that should be from which we want to find seeds. This is done as geometric accelerator structure so that we don't need to test all of the combinations of space points to form a seed. And since this is a 2D grid, I do believe that in a single bin, the space points are pre-sorted in R. So this grid that you see on the right would span the detector volume. And then the seed finding is started by iterating over a middle space point of the final triplet that we want to find. And then we iterate over the possible bottom and top neighboring space points in that bin and in the neighborhood bins of the grid. Then the doublets, in the first step, doublets are formed by applying a certain number of criteria, for example, distance from the space points to the middle space point, compatibility with the IP, and so forth. And from all of those doublets, then triplets are formed with compatible middle space point, and then later on filtered according to which of these triplets will very likely produce good tracks. And then following the seed finding step, we have the track parameter estimation step, which takes the seed triplets and infers an initial track parameterization from it local to some module, which is essentially equivalent to the ACTS implementation at that point. And then on the GPU, the problem has been very similar to that in the clusterization. It's not known a priori how many seeds there are, how many space points will be filled into a single one of those grid bins. And in that sense, it is running the succession of find and counting kernels again in order to be able to do the memory allocations. And as I mentioned before, this is still more efficient than what has been done in ACTS before, where essentially a memory was allocated for every kind of combination that could be. So this, what I just described is more or less the canonical way of doing this, which is very close to what's in ACTS, but there's also a more R&D-like path that has been implemented. So there's the idea of connected component analysis, where an additional analysis step can already be applied on the cells while we're in the labeling phase for the cells to a single cluster. So this can be, for example, in the measurement creation, parts of the measurement creation. And then the clusters themselves don't need to be provided as output anymore. And this saves a lot of memory operations. And then it uses a different algorithm called FastSV, which transforms this problem from a sparse problem, so where we have very little activations over a large sensor matrix, to a graph problem. And since it does different scheme of partitioning, is also better used for better suited for parallelization. And then there's also another seed finding implementation that uses a KD tree internally instead of a spatial grid. And that KD tree splits the detector region successively in R5Z into orthogonal search regions. And then the seed finding is done on range lookups on that KD tree. And one advantage here is that we don't need to pre-compute grid bin capacities, but on the other hand, we need to do the building of the KD tree. So there's a bit of a trade-off there. But these implementations shown, I think, some promising results already. Okay, and then coming to the DETRAY project real quick. So DADRAY is supposed to provide a tracking geometry description that is more realistic than what we've seen before with the telescope geometry. In fact, it will be able to model everything that ACTS also able to model, and it will do this completely without runtime polymorphism, so no virtual functions. It has been written in a way that all of the containers in that detector are flat, and the interlinking of the geometry objects not done via pointers, but index-based. And then, of course, we want to do this heterogeneous. So a large part, or actually all of the core implementation is both usable in host and in device code. And the model of DADRAY, I already mentioned it, is that our classes are templated on the container type, either STL or VecMem. And then the memory allocation is done in the background with VecMem memory resources. And the data structure, the tracking geometry can then be built host side once and then moved to the device where it's essentially static over the rest of the track reconstruction chain. And the entire detector can already be passed to the device via a single view object right now. So quickly, the geometry model in DADRAY is that we have larger subvolumes in the detector, which are defined by their boundary surfaces, which at the same time interconnect different subvolumes in the detector that would, for example, model the layers in Silicon Tracker. Then the surfaces themselves are implemented by their affine placement transforms in the geometry and by a boundary mask in surface local coordinates. So you can see that on the right, there would be a rectangular surface in a local 2D Cartesian coordinate system, or a ring surface in an R5 coordinate system, which is essentially also the coordinate system that the measurements will be given in. And we've done this by defining these tiny shape classes that can be plugged into a mask that will give all of the information of the local coordinate system, how many boundaries there are for a rectangular shape, for a ring shape, and so forth. And plugging these masks as templates into our classes essentially alleviates the problem with the polymorphism. But it leads to a different problem, which is that we need a different container for every one of our surface types. And we've implemented this with tuples and index-based tuple unrolling, essentially. Right, and then the portal surfaces I mentioned are actually the same thing as the surfaces, only that they keep an index to link against other volumes. And in a very similar way, we've also added the material to a surface via an index into a tuple and an index that defines the material type. And then we have an additional tuple where we unroll essentially the material type for every surface. It's a bit involved, but it works. So we have in DADRAY then a central detector setup where all of the geometry data is held, where also the magnetic field data is held. The detector manages all of the moves between host and device, and then it provides the interface for the track state propagation for all of the other classes. We have a testbed geometry currently, which is just a pixel detector of the ACTS generic detector. So it's a very simple silicon detector setup. But it has different shapes in a barrel. It has trapezoids in an end cap, and it has gap volumes in between so that we can navigate from sensitive surface through an empty volume to the next layer of sensitive surfaces easily. And these plots are actually from ACTS. So in ACTS, a similar geometry model is experimentally included right now that has simplified what the ACTS geometry description has been before to this volume, boundary surface, and sensitive surface model that I just described. All right, so the meat and bone of DADRAY is, of course, to propagate the track states during track reconstruction through that geometry. And it's doing this with a propagator that calls a navigator and a stepper. So the navigator will figure out where in the tracking geometry we are, how we get to the next either volume boundary or surface. And then the stepper will integrate the track state to that surface through the magnetic field. And then we have a number of actors and aborters that run in the meantime that can perform various other tasks, like, for example, material interactions if we encounter a surface, or the Kalman filter, I believe, is also containing an actor. Yes. And then the navigation flow will guide us from one volume into the next volume, where we then do the sensitive surface lookup. And quite similar to the seed finding, we don't want to do this for every surface in that volume, but we will also apply a spatial grid as accelerator structure. In principle, this can be any kind of accelerator structure, but currently we are looking into grids as they are also used in ACTS. All right, and then the field integration I already mentioned. We have an inhomogeneous B field in general, so there's no closed analytical solution for a helix. And we need to do an integration for our track state, which is currently done by an adaptive Runge-Kutta algorithm, which gets the distance to the next target surface from the navigator. Then, depending on the integration error in the integration step through the B field, it will adjust the step size and perform the advancement of the track parameters along this step size, and also compute a transport Jacobian for the track parameters along the way. And then we run the material interaction and covariance transport in DEDRAE 2. So at every surface that we encounter that has material, we're computing material effects, like energy losses, multiple scattering, and so forth, and add this to the track state covariance, which is then also transported through the geometry by transforming from local coordinates to global coordinates, transport Jacobian, and so forth. And in the end, we can set together a full Jacobian transport matrix for the covariance and transform the covariance from the initial track state to the final one. Okay, and all of this, like material interaction, covariance, transport, and so forth, is also implemented as actors already. And then last but not least, there's the COFFEE library, which we will use in DEDRAE for the inhomogeneous magnetic field description at one point. So this is actually a library that provides a generalized vector field description, not just for magnetic fields, but for any kind of vector field that you could come up with. And it's doing this by type composition at compile time. So there are a number of different elements that you can stick together to describe your vector field, like different memory backends, like STD array, for example, as a very similar one, then layouts of how to put the vector data into memory. So for example, in a strided layout or in spatial curves, then you can put boundary behavior on the edges of your vector field. You can wrap interpolations around that, which is very important for the magnetic field, and also transforms. And then, the field itself is stored in a COFFEE field. And the type of that field defines the layout and behavior. And this is accessed by a view. And it can be moved the device actually quite simply just by passing the field to the constructor of a device field type. And it will do the move for you in the background. Yes, and I already mentioned this will be used in DEDRAE quite soon, hopefully, for the Atlas B field, for which there's already a nice render available as a little teaser. Okay, that brings me to the summary. So in the ACTS project, we have a pretty diverse parallelization R&D project at this point, which spans almost the entire track reconstruction chain, because the Kalman filtering is still work in progress, but in the end it will. And this starts from very technical libraries like polymorphic and composable memory management via VecMem, which allows us to target different device backends, over linear algebra implementation abstractions that can be plugged in to our code and then benchmarked. This includes the device-friendly and detector-independent geometry description of DETRAY, which also provides track propagation. And then I forgot a point, sorry. And finally, we have Track2C, where it all comes together, where we go from input cell activations to final tracks. So all of that is already there. The outlook on this, well, very recently in the algebra plugins implementation, we've looked at integrating the FASTER library, and we plan to revise the VC plugin. So there's been some micro benchmarking on different linear algebra implementations, and FASTER seemed to be a very promising candidate, and the integration of that plugin is ongoing. It's not currently working in DETRAY and Track2C, but hopefully soon. Then for DETRAY, we plan on adding Coffee fully. It's currently already used for the homogeneous B field, but obviously we want the full Atlas B field. And then we are heavily working on JSON-based I/O for the tracking geometry, so that the new experimental tracking geometry from ACTS can be dumped and read in directly to DETRAY, which will give us access basically to any tracking geometry that's already described in ACTS, like hopefully one day the ITK. And then in Track2C, the implementation of the Kalman filtering is ongoing. This will be the Kalman track filter, but also the combinatorial Kalman filter. Currently, I think the Kalman filter, there is a CPU and a GPU implementation work in progress. And then next step will be to look a bit more deeply into how to do thread synchronization and how to put the, actually it's already ongoing, the benchmarking of putting the entire chain together. So in Track2C, the benchmarking and profiling's already seen a lot of work. In DETRAY, well, there's very little work done to that, and in algebra plugins, we have this external micro benchmarking, but also not much of a benchmarking. So this is one big point that we want to tackle in the near future. And yeah, that brings me to the end. So thank you very much for your attention, and open for questions.
Yeah, thanks so much, Johanna. It really is an impressive amount of work which has been done to get all of this going. So indeed, we have plenty of time now for questions. If anyone would prefer to ask a question by typing it, then we have some live notes. I put the link in the chat if you want to go there. Otherwise, just raise your hand in Zoom. And indeed, I see that Ben is the first person to raise his hand. So please go ahead, Ben, with your question.
Apologies if this is a boring one. The JSON-based tracking geometry reading, is that specifically going to enable using a full, say, Atlas ITK detector geometry, or another detector in particular that it's targeting?
No.
And if it's not, is there a timescale for the Atlas ITK geometry?
Well, the last one is a good question. So first of all, the JSON I/O is, like ACTS in general, not detector specific. So it will be a generic I/O. So you should be able to read in any kind of tracking geometry that's already there in ACTS and has been dumped into JSON directly into DETRAY. So DETRAY is flexible enough to model all of these tracking geometries. Now, the timescale for the ITK is a bit, that's a bit difficult to say.
No worries if you don't have an answer. I just wondered.
I can answer this. If you go back to the slide on the geometry, we can see the Open Data Detector version.
The ODD one, yeah.
Yes, this one. So that exists already. That's not so far away from the ITK. It exists yet on the ACTS side, but is not fully merged in. The big change here, what we have done is we learned from DETRAY, where the geometry model of ACTS was re-implemented, that the concept of surface layer volume, which is a three-body problem, can be reduced to surface volume without compromising any of the description. Now that is quite a big rework, and that's why it's called experimental. So there's a new parallel geometry stream in the ACTS core that will basically implement that, while all the top level tools that are surface listeners, they are relatively untouched by this, because it's just how the surfaces are provided. Now, that's really the cracking point. When this is validated, to change that from the open data detector to the ITK or any other cylindrical disc-like detector is gonna be a bit of dirty handwork, and make sure that everything is okay, but doesn't need functional or additional code, hopefully. Well, shouldn't, because the shapes are all defined. So
yes,
pretty confident that we have that in the first quarter of next year.
Yeah, so it's true. Conceptually, everything is there. We're writing really on the nitty-gritty code to do the I/O right now, and some technical stuff that I think needs to be changed in that way. But none of that is a game stopper, really.
Sorry, I wasn't meaning to chivvy you along at all. I just just wondered how things are going. When you say dirty handwork, though, you mean specifically that you would need to implement this by hand, or just that it might need some tweaking once it's in?
No, this already works quite well. So all of this, what you see here, is essentially there. There is some assumptions we've made in DETRAY in the past for these simpler geometries that we might need to retract again. But this is, well, this will be done transparently inside of DETRAY, and
Ben, it's more to check. So there is this, if you go one slide before or somewhere, where you can see the surface ordering in the grids. I don't know where you had this. This needs checking. There's this one, that you see this is we have developed this display which basically shows you when you arrive on one of the compound structures, which are the candidates that are provided by the navigation. So that to some extent you can do auto generate, but you need to check it, because one shoe fits all for geometry is it's impossible.
So it is literally just checking that nothing weird happens. Okay, cool. Thank you.
Yes, and there's one of the technical aspects is that other than track2c, what DETRAY needs is an entire collection of these grids, because a detector might have hundreds of them, and all of them need to be moved to device. So there was a bit of a re-implementation of the grids in order to do this in more flat containers, and how to put the surfaces into the grids and how to fill the grids right now. This is kind of the step that's missing. The rest of the geometry description should work for the ITK already.
Cool. Thanks a lot.
That's great. Thanks a lot for all of the clarifications. So let's carry on with the questions. Anything else that people would like to ask? I'm not seeing any other hands go up, so let me ask my one. It's a bit the $6 million question. Do you have an early idea of what the performance is? I mean, how fast can we actually fit tracks on the GPU? Is it something that looks like, oh, hey, this is really good, we should carry on with it? Or is it like, we need to optimize this again?
Well, so
what's your feeling?
I can answer this mainly from the DETRAY side. So there the benchmarking has been a bit sparse, and there's been no real profiling on the code. So we benchmarked this against a multi-threaded CPU, and there the speed up towards the full GPU, there was a slight speed up there, but not too much. And we need to understand basically what's going on there, because this code in DETRAY is running on the device as is running on the host. So it's literally 1-to-1, and there has been no optimization to what the device memory access patterns and so forth would be. So for DedRay, this is very much in the open right now, I would say. For TrackCC, I don't know, there are people here who've done more on the benchmarking and profiling of that chain who might answer this question.
I think I can take this. Yeah, I think in TrackCC we've already seen some results which are definitely promising. Especially when you're dealing with events with a very large amount of a very large pile of a lot of data coming in, where we've seen that GPU can definitely be an improvement. But there's also, when you're looking at lower pileups, not so much. And we know for a fact that there's also still a lot of way to go, a lot of ways to improve, and we're also working on that right now.
Great, thanks a lot for the clarifications. Next hand was Patrick, so please go ahead and ask your question, Patrick.
So I heard profiling mentioned, and I'm in charge of looking into a profiler for the GPU. I'm just curious, as when you say profiling, do you mean actually running like NVIDIA's Insight systems or whatever the equivalent AMD is, or are you just talking about getting event throughput, that sort of thing?
So on DedRay, Insight would probably be the first step because none of this has been done yet. On TrackCC, I think it's actually further. There has been some profiling with Insight and so forth, but there's also throughput tests available already.
That is correct.
I would say on this that in TrackCC, what we are trying to do at the moment is to actually look into the individual kernels. So for NVIDIA GPUs, this would be the Insight Compute sort of profiling. That's sort of our big challenge of trying to understand why or how the kernels themselves could be further sped up. On how we can speed up the scheduling of kernels and the scheduling of memory copies, I think for that we have by now a fairly good understanding of, from just Insight systems.
Yeah, so for
Sorry, I didn't mean to interrupt. Sorry, we're suffering from lag again. Go ahead, Joanna.
No, I just wanted to add that for the DedRay side, we're still running a single humongous kernel for the propagation and one thread per track. And that's all that's going on right now. And the memory movement is done in managed memory. So what the impact of that is, we don't know yet. And there's a lot of also even data duplication in the way the tracking geometry is put into memory. So all of these things haven't been investigated yet and might very much be the reason for the lack of a clear speed up of the GPU that we're seeing right now. So this is what I meant with profiling and investigating this further before we can make an actual statement here.
Sure, of course, John.
Just one more follow-up question. So have you made a CPU to GPU comparison, or is that not really possible? Because that's another kind of question that comes up, like in the reconstruction process for CNS is offloading this to GPU worth it, considering the memory transfer time? You guys have some way of measuring that?
So again, for the DedRay side, I did these ultra preliminary benchmarks with Eigenalgebra plugin on the left and the STD array-based plugin on the right. And it's a bit misleading in these plots is that Eigen actually seemed to be, I think, a factor of 2-3 slower than STD array, which we don't understand right now. And then you can see the GPU for the full propagation loop in orange and the multi-threaded 24-core CPU for the propagation loop in red, and then number of tracks on the x-axis. So this is what we're seeing here. And yeah, well, for Eigen, there's some speed up at some point. For STD array, not really. So.
Okay, thanks very much.
Probably Patrick, to answer your second question you had there, this is deliberately designed that we can run the same code on host and device. So you ask if this is possible. Yes, this was one of the premises of the project, that while single source code is probably too bold, but it's a largely, I don't know, core code that is identical, and then cross compiled.
And in terms of memory transfer, again, this is managed memory, so this might be hitting us for a small number of tracks quite a lot. What happens if we copy the thing completely to device? We'll see, but in general, the tracking geometry at least should be able to just copy it onto device once and then just keep reusing it to the reconstruction. So.
Okay, thanks. Yeah, I could ask a lot more questions, but I don't want.
Yeah, for the for the TrackCC side of this, again, I would invite other people to fill the blank.
That's great. Thanks, Joanna, and everyone else. Francesca, you had your hand up and then it went down just as we were concluding that discussion. I don't know if you still wanted to ask something else.
I think I got the answer. I got the answer. Yes, thanks.
Okay, that's very good. All right. So, any last questions that people would like to ask before we close? Ben, again, why not? Go ahead.
Since no one else was there. So no need to go into detail, and feel free to tell me if I'm just asking an overly vague question. But in terms of just your general approach, how do you compare TrackCC and what it does to other GPU tracking projects like Patatrack or the Atlas Trigger GPU prototype that existed a few years ago? Yeah, again, no need to go into detailed comparisons or performance or anything, just like strategy-wise, how do you compare or contrast these projects? Do you have a feeling for that?
Yes, I think I would pass that question more on to the people who are working more closely on TrackCC.
So the premise of this project, of this R&D line, was to approach the hammer and nail question from the fact that we have a solution. Can we port the solution onto the GPU? Basically, really, without making compromises in, we would like to have the exact quality of the magnetic field. Would like to have the exact same quality of the geometry. We would like to run the CKF, which is the probably most difficult one because it's such a branching engine. And we would like to see, can we port that onto the GPU, and not asking the question which algorithm would fit onto the GPU. And I think that is the sort of distinction in the project here.
Cool. That's exactly the kind of answer I was looking for. Thank you. Just to understand the big picture. Thank you very much.
Okay, great. Thanks for the answer, Andy. Okay, last call for questions. Nope, I'm not seeing any. In that case, let's thank Joanna again. That was a very interesting presentation, and we had some nice discussion as well. I was very pleased to see all of the progress there. So with that, I think we can close the meeting. Thank everyone for coming along, and we look forward to seeing you in 2023. And do enjoy your winter break. All right.